In this module we will tackle magnetism and the phenomenon around it. Magnets are familiar objects that we use in different things such as motors. There are two types of magnets, the permanent and non-permanent magnets. Early discovery of the phenomenon of magnets goes back to the early 2,500 years ago in the ancient city of Magnesia. There are naturally occurring types of magnets found in nature such as magnetite or a form of iron oxide where it has magnetic property. This magnetic property is the phenomenon where a magnet exerts a force on metal objects such as iron and other magnets. We know this because when we bring close metallic objects like nails close to a magnet, you feel a tug of force that brings the object close to it. Bar magnets or magnets in general have two poles all the time. The North and South Pole. The North Pole is usually referred to as the positive pole and the South Pole is the negative pole. Bar magnets are permanent magnets that continuously exhibit a magnetic force. Here we have three scenarios for bar magnets with the behavior of its magnetic field lines. For the first case, letter A, the single magnet shows an attraction between its poles. The blue lines here represent the magnetic field lines which are similar to the electric field lines. The magnetic field lines represent the direction of the magnetic force. The lines are drawn from the north or positive pole towards the south pole or the negative pole. For case B, we have two unlike poles and the case here shows an attraction A between them and binds together as much as they can. For case C, we have two like poles and it is expected they will have a repulsive interaction and will separate as much as they can. So like poles repulse one another and unlike poles attract one another, which is the same for like and unlike charges. Magnetic field lines continuously flow from the magnet. It starts from the North Pole to the South Pole. Here we have a demonstration of the magnetic field lines and a compass is moved around it. The direction of the compass is changed when it is moved around it and reorients itself to point to a specific pole that is opposite to it. Compasses are also tiny magnets. Our planet is considered a magnet, which is why we can navigate using a compass to point us towards the geomagnetic North Pole, which is actually the magnetic South Pole as shown in the animation. This attracts the North Pole of the compass. The angle between them is around 11.5 degrees. In 1806 Ørsted became a professor at the University of Copenhagen, where his first physical researches dealt with electric currents and acoustics. During an evening lecture in April 1820, Ørsted discovered that a magnetic needle aligns itself perpendicularly to a current-carrying wire, definite experimental evidence of the relationship between electricity and magnetism. The behavior of the compass will align with respect to the direction of the current. Here we have a demonstration of the experiment. As the wire is connected together allowing the flow of current, we see the compass deflecting. This is because the flow of current produces a magnetic field which the compass reacts to since it has a magnetic material attached to it. This type of magnets are called non-permanent magnets, where it exhibits a controllable magnetic field by adjusting the flow of charges. Deflection of the compass is observed as the current flows through a wire in different directions. As the current flows or a charge flows through a wire, it generates a magnetic field. The direction of the magnetic field is circular in nature based on the shape of the wire, and its direction can be determined using the right-hand rule. The thumbs point in the same direction as the current. The other fingers curl around the wire and it shows the direction of the magnetic field. Counterclockwise direction when the current is pointed upwards and clockwise when the current is pointed downwards. Let us recall the properties of the electric field and compare it with the magnetic field. Electric field. Number 1, stationary charge produces an electric field. Number 2, the electric field exerts a force on a charge q around the field. Magnetic field. Number 1, a moving charge or current flow produces a magnetic field. The electric field is also present. Number 2, the magnetic field exerts a force on a charge q around the field. Its unit is called Tesla, and 1 Tesla is equal to 1 Newton per ampere times meter. Or in terms of Gauss, we have 1 Gauss equals to 10 to the power of minus 4 Tesla. Four characteristics of the magnetic force on a moving charge. Number 1, the magnitude is proportional to the magnitude of the charge. Number 2, the magnitude of the force is also proportional to the strength of the magnetic field. Number 3, the magnetic force depends on the particle's velocity, and when a charge is not moving, then it does not experience a magnetic force. And number 4, the magnetic force does not have the same direction as the magnetic field, but it is always perpendicular to the magnetic field and velocity. Taking all these four characteristics, we write the magnetic force as shown in equation 1. Here we see a charge moving by some angle phi with respect to the magnetic field. The direction of the magnetic force is oriented perpendicular to the magnetic field and velocity v, and we can write the expression 2. When the charge is moving parallel where the angle between the magnetic field and velocity is 0, the magnetic force is 0. And when it is 90 degrees with respect to the magnetic field, then the magnetic force is maximum. To determine the direction of the magnetic force, we can use another type of right-hand rule. First, put the tails of the vector arrow representation of the magnetic field and velocity together. Second, put the base of your palm going in the opposite direction with the magnetic field line. Third, curl your finger to the direction of the velocity pivoting at the tails. And fourth, the thumb points the direction of the magnetic force, and note that this is perpendicular to the plane where the magnetic field and velocity are. When we replace the charge with a negative charge, the direction of the magnetic force goes in the opposite direction, but still perpendicular with respect to the magnetic field and velocity of the negative charge. Here we have two equal charges moving in the same direction with respect to the magnetic field A, and both experience an equal amount of force but opposite in direction. The ability of magnetic fields to exert movement on charges which essentially produce current flow is the concept that governs electricity production, such as in hydro dams. Here we have a magnetic field going inwards of the page. The mark X here indicates that the field is going inward. A charged particle moves in that field. The magnetic force is shown here. A positive charge shows that the magnetic force is pointed upward. The particle's motion is affected because of this force, and it will be deflected. This will deflect the particle to move upward like manner as shown by its trajectory. This will actually cause the particle to move in circles. Here we replace the charge with a negative charge, and we simply reverse the direction of magnetic force, causing the particle to move in circles but in a clockwise manner. Going back to the behavior of the positive charge moving in a magnetic field, the shape of the trajectory as mentioned is circular, but it looks more of helical shape as shown A here. We can also look at the radius of this helical trajectory by considering the components of the velocity vector and its components. We have the velocity perpendicular to the magnetic field and velocity parallel to the magnetic field. If we compare the two components, the velocity that is parallel does not contribute to the radius of the trajectory but only the perpendicular velocity. We recall the centripetal force equation or the radial force. We have equation 3. We equate this to the magnetic force equation with the 90 degrees angle difference, and we get an equation for the radius of the helical trajectory of the charged particle in a magnetic field. The particle's trajectory is circular in shape, with which we can extract other physical quantities that are related to circular motion. Note that the particle's motion is constant under the presence of a magnetic field, where the velocity is given as equation 5. Here we can rewrite this into the expression for angular velocity as shown in equation 6. Substituting the value of the radius r obtained earlier for the helical trajectory, we get an expression for the angular velocity for the charged particle moving constantly under the magnetic field shown in equation 7. From the expression of angular velocity we can also obtain other quantities such as the frequency, which is given in equation 8. Substituting the value of the angular velocity to this, we get equation 9. This frequency is called the cyclotron frequency. One interesting study with particles moving in magnetic fields is its applications in discovering other particles by using devices such as atom smashers or super colliders. A particle accelerator is a machine that uses electromagnetic fields to propel charged particles to very high speeds and energies. An example of simulated data modeled on the collision of two protons. Particles are produced after this collision, such as the Higgs boson, hadrons, and electrons. The lines are the possible trajectory of the particles. Earth's magnetic field acts like a protective shield against charged particles coming from the sun and space radiation. The magnetic field produces donut-shaped regions around the Earth, and these regions are called Van Allen radiation belts. When the particles from space enters Earth's atmosphere, they produce reaction with it, causing the formation of northern and southern lights. Shown here is the aurora borealis. Magnetic flux is similar to electric flux, and it is related to Gauss's law. Here we use a surface where the magnetic field passes through. We consider the magnetic field that is perpendicular to a small area d. As shown in the figure, the magnetic flux varies with such type of surface area. The magnetic flux is then given as equation 10. The total magnetic flux through the surface area is then given as an integral function which sums the areas, and it is given as equation 11. If the magnetic field is constant, then the angle phi is the same and the magnetic flux is just given as equation 12. Note that dot products like this give a scalar quantity. So the magnetic flux would be a scalar product. When the magnetic field is also constant and it is perpendicular with respect to the area, then we have the magnetic flux as shown in equation 13, which is 0. This means that only the magnetic field passing through the area produces magnetic flux. Comparing electric flux and magnetic flux. We recall the Gauss equation for electric flux. It is shown here in equation 14. For electric flux, it is dependent on the charges contained inside the Gaussian surface. Here we have a positive charge Q contained inside the Gaussian surface, so the net flux is given as equation 15. For magnetic fields where magnets are always dipoles having a north and south poles even if they are cut multiple times, the magnetic flux through an enclosed surface is always zero as shown in equation 16. This is because the direction of the magnetic field lines always goes back to the magnetic and appears to have no beginning and end. This expression is also called Gauss' law for magnetism. When a charge moves where both magnetic and electric fields are present, the charge experiences a force due to these electromagnetic fields. This force is called the Lorentz force, which is given as equation 16. Shown in the figure, here we have a charge moving between a charged parallel plate where the charge experiences an electric force. The charge is also subjected to the magnetic field that is going into the page and experiences a force from it. Shown here are the forces arranged in opposition with one another. When the forces become equal, the net force is zero we have here. This will result in a speed v with no deflection, and its value is given as the ratio of electric and magnetic field as shown here in equation 16. The device that does this is called a velocity selector. Only particles with the speed equal to this ratio can pass through without being deflected. Thomson's E/M experiment conducted in 1987 to determine the value of the ratio of electric charge against its mass. Here either a positive or a negative charge can be used to determine the ratio, since it cancels out at the end as shown by the equation. As the charges flow through a vacuum tube, it is exposed to electric and magnetic fields. The particle is then detected when it hits the screen. The speed of the charge is related to the electric potential energy, which means that the electric potential energy is converted to its kinetic energy given as equation 17. We then rewrite this to get the speed equation 18. Equating this to the electric field and magnetic field ratio, and we get the ratio of the electric charge over its mass shown in equation 19. The ratio was measured to be about 1.75 times 10 to the power of 11 coulombs per kilogram. This experiment was the first time to experimentally measure the mass-to-charge ratio of an electron. This experiment also showed that electrons are particles having mass and a charge. 15 years later, the American physicist Robert Millikan succeeded in measuring the charge of an electron. With that information, they were able to determine the mass of an electron. Here we have a simulation where a magnetic field is generated by a non-permanent magnet. When there is no potential difference given by the EMF source, there is no flow of currents and there is no magnetic field produced. When we put a potential difference across the wire, it generates a magnetic field due to the flow of charges. We also see that when we increase the voltage difference, the magnetic field also increases as shown here. Reversing the polarity of the EMF source also alters the direction of the magnetic field. In this part we will talk about how magnetic fields are produced through conducting materials. Here we have a positive charge moving through a wire with speed v, which is the drift velocity. The magnetic field exerts a force on this charge as shown on the figure, and using the right-hand rule it is oriented to the left with respect to the direction of the particle. This magnetic force along a current-carrying wire is the basis for electric motors. Shown on the inside of a motor is a wire where current flows and creates a magnetic field that creates a force that causes a motor to turn. For a single charge, the force is given by equation 2. When there are several charges moving across the wire, then we write the magnetic force as shown in equation 21. Since we are dealing with charges moving in a volume, the amount of charges is written as a function of the number of charges per unit volume. So for this short segment wire with length L and cross-sectional area A, then the number of charges is given as equation 22. So the total magnetic force can be expressed as equation 23, where the enclosed term is the current density. Current density is the amount of charges passing through an area and can be written as equation 25. Note that V and Vd are the same. Recall Vd as the drift velocity, which is the velocity of a charged particle in a wire. So we can write the net force as equation 26. Where B here is the perpendicular to the wire or drift velocity, so we rewrite it as equation 27. Also in terms of cross product we have equation 28. But wires are rarely straight, and so we write an expression for wires that are curved, and of course we have to apply a differential equation where we take a small segment denoted as dl, and shown here is the equation for the magnetic force shown in equation 29. We can then integrate this function to get the total magnetic force. Like for this curved wire, we can apply a line integral function. We note that the current is not a vector and the direction of flow is defined by the shape of the wire. So it is described by the dl. Even if the conductor is curved, the current will be the same at all points along its length. Here we have a current carrying conducting wire in a closed loop. It is subject to a magnetic field going upward perpendicular to the xy plane. Forces are generated along its sides and appear to be equal in magnitude but opposite in direction. The forces along the y-axis will not cause the body to rotate. The forces along the x-axis will cause the body to rotate along its center clockwise. Note that the magnetic force direction is done using the right-hand rule, and we see that it is perpendicular to the length A, and we get an expression for it as shown in equation 31. Recall the equation for torque, which is given as equation 32. For a single torque due to one of the forces, it is given as equation 33. The net torque for these two forces, which both will cause the body to rotate in clockwise direction, we have equation 34. Substituting the value of the force, we get equation 35, where the torque is proportional to the scalar current and the cross product of the area vector and magnetic field. The factor of current times the vector area is called a magnetic dipole or magnetic moment, shown in equation 36. This is synonymous to the electric moment. It is oriented in the same manner as the area vector, which is perpendicular to the plane of the conducting loop. Then we can write the torque expression in terms of the magnetic moment as shown in equation 37. Since there are two faces for the area, we use the right-hand rule to point the direction of the magnetic moment. The direction of the magnetic moment is oriented using the right-hand rule, where the thumb points the direction. The curl of the four fingers follows the direction of the current. In this scenario, the conducting loop is oriented perpendicular, so the magnetic moment and the magnetic field are perpendicular. The net torque then is shown in equation 38. In this case the loop is now lying on the x and y plane where the magnetic field and magnetic moment are oriented in the same direction, so the angle between them is 0 or 180. The net torque is 0 as shown in equation 39. Potential energy for magnetic dipole. Recall the expression for work but in derivative form as shown here in equation 40. Where work is a function given in equation 41. The potential energy is then obtained from the work function and it is given as equation 42. The 0 point of the potential energy is arbitrary, so we let the angle 90 degrees be 0 potential. So evaluate the integral function from pi/2 to theta. The potential energy is 0 when the magnetic dipole is perpendicular with the magnetic field. Potential energy is minimum when they are parallel since U is negative. When the angle is 180 then it is maximum since U becomes positive. When the conductor rotates around its axis it causes changes in the direction of the magnetic moment as shown in equation 46, where it is just twice the potential. Solenoids have an arrangement of closed loop which can multiply its magnetic effects such as magnetic moment, torque, and the potential energy. The parameter mentioned will be directly proportional to the number of coils as shown here. Magnetic moment equation 47, torque equation 48, and potential energy equation 49. Here they are simply a multiple of n times its single coil version. The magnetic field lines for a solenoid is just the same as that of a permanent magnet, but a key difference of how it is able to produce it. The flow of current across the wire produces the magnetic field and we can adjust its strength based on the number of coils. We can also reverse the direction of the magnetic field by reversing the current flow. Combination of solenoids, a non-permanent magnet and bar magnets have produced electric motors that are used in generating electricity and motion in electric vehicles. Here we have a solenoid in the presence of a magnetic field. Recall that torque will be maximum if the solenoid is perpendicular with the magnetic field and 0 when they are parallel. The system will tend to rotate the solenoid into a position where its axis is parallel to the field. The torque will tend to make the solenoid rotate clockwise to align the magnetic moment and the magnetic field. The torque is going out of the page since it is a cross product. Here we have a conducting loop exposed to a non-uniform magnetic field as shown in the figure. In this case the net force is not 0 since the magnetic field is not uniform. Since at each segment dl, the force is different, we take each force as a derivative form as shown by equation 29. As we examine the figure there are basically two types of forces here. First are the forces moving around the wire which are equal but opposite in direction. Second are the forces going to the right. So, if we sum these forces, only the forces moving to the right will not cancel out. Here we have a closer look at the direction of the magnetic force where radial related and right force are originating. The radial force is where the magnetic field intersects the face where the force is oriented inward. The right force is the one side where the wire faces the opposite side of the magnetic field. When the polarity of the magnetic field source is reversed, the radial directed forces still cancel each other and only the forces going to the left are present. Comparing the two, the net force when the magnetic field is going outward, the loop is weaker compared to the magnetic field going inward. This is because the magnetic field farther from the source, the magnetic field lines are farther apart, thus lesser magnetic field. If they are able to turn, then both will turn due to torque. Parallel to the B field. The case for the solenoid turning would be due to the current or moving charges due to the magnetic field. The case for the permanent magnet would be due to atomic interactions. To understand permanent magnets, we have to look into its smaller structure. When we cut magnets, they just simply form into much smaller magnets. At sizes which we call domains, where they form identical structural orientation, they still form some tiny magnets that may be oriented slightly differently, but when exposed to a strong magnetic field will be reoriented. We have to look deeper into the atomic structure to understand how magnets generate magnetic fields. As the electrons move around its orbit, it generates a magnetic field. So we expect that all matter to be magnetic, but this is not what we observe in reality. The reason for this is that there is cancellation of magnetic field effects due to different orientations, such as in the domains where tiny magnets inside an object have different orientation, and the net magnetic field would result in zero. For the atomic model, the pairing of electrons, spin up and spin down, in an orbit matters, and those atoms with paired electrons would. Iron is ferromagnetic and it has 4 unpaired electrons in the d shell or d orbital. Magnetism is a fundamental property like charge. Gold is an example that is non-magnetic, and if we examine its electronic configuration, it has only one lone pair in the s orbital or s shell. Note that there are materials that do not obey this directly, such as magnesium, which has no unpaired electrons, but they are magnetic. The population of the spin up and down electrons changes when exposed to a magnetic field, which causes it to be magnetized and turn into a paramagnetic material. Paramagnetic simply means weakly, and its opposite would be diamagnetic. We know that the magnetic property is due to the atomic characteristics of a material, and we know that in an atom electrons rotate around its nucleus, generating a magnetic field as shown here. The magnetic moment is determined using the right-hand rule, and we see it pointed this way with respect to the flow of current. Note that electrons moving around the nucleus in the opposite direction as the conventional current. We write an expression for the magnitude of the magnetic moment using equation 36. The current is the ratio of charges over time, and we see here that the charge refers to a single electron charge shown in equation 50. We replace the time with a period t since it is moving in circles, and we know that the distance for a periodic motion is given as 2 pi r. And we write the velocity as a function of this and substitute this back to the orbital magnetic moment, and we get equation 51. So the strength of its magnetic field depends on the speed of the charge, the radius, and the charge of the particle. In mechanics, we recall the physical quantity called the angular momentum, given as equation 52. The direction of angular momentum follows the right-hand rule, but instead of the current it follows the mass, which is the direction of the electron. For electrons, the angular momentum is opposite with respect to its moment. We write the angular momentum for the electron moving around its orbit as shown here. Then the orbital magnetic moment is also expressed in terms of its angular momentum as shown in equation 53. Unmagnetized iron bar has randomly oriented magnetic moments. Magnetized iron bar has aligned magnetic moments pointing from the south pole to the north pole. A magnetic field creates a torque on the bar magnet that tends to align its dipole moment with the magnetic field. Hall effect was discovered by Edwin Hall in 1879 and showed the production of Hall voltage whose application is used in fast sensors. Here we have a material where electrons flow undeflected and go straight. When a magnetic field is introduced, the electrons are deflected and begin to accumulate on one edge. This will form an electric field due to separation of opposing charges and an electric force exerted on the charge. When the charges at both ends are full, then the electron will no longer be deflected. The force experienced by the charged particle is shown here. If the particle becomes undeflected and flows normally between the electric field, then the force exerted by the magnetic and electric field are equal. Here we can calculate the drift velocity of the particle using equation 16, which is the same formulation obtained earlier for charges moving in electric and magnetic fields. If we measure the electric potential difference from points A to B, we would get a voltage called the Hall voltage or Hall EMF, which is a transverse potential difference. This discovery was applied to semiconductors, which enabled us to determine the type of dominant charge carriers if they are carried by electrons called N-type semiconductors or carried by holes called a P-type semiconductor. Holes are just vacant positions left by electrons. The Hall effect equation is useful in determining several factors such as the concentration N, current density, magnetic and electric fields in both conductors and semiconductors. Typically the charge used here is the electrons, but we set this to absolute value, thus this equation is usable for both positive and negative charges. Replacing the negative charge with a positive charge will still result in the same effect as shown here, which makes the calculations obtained earlier useful for positive charges also. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyslearningstuff@gmail.com. You may review the slide on YouTube at @diyslearningstuff. Note, please do not forget to use your school email. Also write your complete name and a class section. Thank you for listening and see you next module.